Hello and welcome to another exciting pre-calculus math video. This video will begin section 2.5. This is going to take place over 4 days, 4 videos. This is a pretty juicy section. We're going to use the fundamental theorem of algebra to determine the number of zeros that a polynomial function has. We will find the rational zeros of polynomial functions, not the irrationals. We will find complex zeros that come in conjugate pairs. We will find zeros of polynomials by factoring. We've been doing that for a while. We'll talk about Descartes' rule of signs and the upper and lower bound rules to find the zeros of polynomials. And we'll find the zeros of polynomials in real-life applications, because what real-life problem cannot be solved by factoring? And here we go. The fundamental theorem of algebra. In the complex number system, every nth degree polynomial function has precisely n zeros. This important result is derived from the fundamental theorem of algebra, first proved by the German mathematician Carl Friedrich Gauss back in the 1800s. And this theorem says if our function f of x is a polynomial of degree n, where n is a positive number, then our function has at least one zero in the complex numbers system. Using the fundamental theorem of algebra and the equivalence of zeros and factors, we can attain the linear factorization theorem. And this theorem says if our function is a polynomial of degree n, where n is positive, then our function has precisely n linear factors. Remember, a linear factor is x plus or minus some number. And there could be a number in front of the x, like 2x plus 1 or a half x plus 3. If it's x to the first, it's a linear factor. And think, if we have a x squared minus 3x plus 2, that would factor down into x minus 2, x minus 1. And this is a second degree polynomial, and it has precisely 2 linear factors. And if we had one that was a cube there, it would have 3 linear factors, so on and so forth. So here, example 1, let's see, find the zeros of the polynomial. And it says, A, the first degree polynomial function, x minus 2. They're asking how many zeros does it have. It has exactly 1. Exactly 1 0. And this one, we could even, set that equal to 0, and we could say that 0 is at x equals 2. Letter B. The second degree polynomial function, x squared minus 6x plus 9. Well, we could factor that into x minus 3 times x minus 3. It has, for this one, exactly 2 zeros. Exactly 2 zeros. But I'm going to put in parenthesis, it's repeated, because we could write that as x minus 3 quantity squared. X minus 3 quantity squared. So it is a repeated 0, but there are 2 of them there. And remember, this multiplicity says on the graph we would bounce off the x-axis, not cross it. Letter C. This third degree polynomial, x cubed plus 4x, well, we could factor that into x times x minus 2i, x plus 2i. Let's see here. If we factor out an x, we get x squared plus 4 equal to 0. Well, we can set the first x equal to 0, and we can set the x squared plus 4 equal to 0. And then we would subtract 4 from each side, and then we would take a square root. Now remember, a negative under a radical, that negative will just escape as the imaginary component I. So we could write that as 2i plus or minus when we square root both sides. And there's our factorization up there, x plus 2i, x minus 2i. Again, the big idea here is it's a third power polynomial. It has 3 linear factors. Oops. The rational zero test. It relates the possible rational zeros of a polynomial having integer coefficients to the leading coefficient and to the constant term at the end of the polynomial. So here, this is kind of with all the script and subscript stuff. Here's our polynomial's first term, a sub n. That's just some number like 3 or 4 or 5. And then we have this x to the nth power. Here at the end, we have our constant a sub 0. So it says here, if our polynomial has integer coefficients, then every rational zero of our function has this form, p divided by q. P, the numerator, is the factors of the constant at the end. The q, the denominator, are the factors of the leading coefficient. So you're going to take this number at the end, the constant, figure out its factors. That will be the numerator in your fraction. Q, you take the leading coefficient at the very beginning, what are its factors, and put those in the denominator. All those possibilities are your possible zeros. So to use the rational zero test, we should first list all rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. Having formed this list of possible rational zeros, use the trial and error method to determine which, if any of them, are actual zeros of the polynomial. Note that when the leading coefficient is 1, the possible rational zeros are simply the factors of the constant. And when they say a trial and error method, a lot of times we'll just use synthetic division. We'll try the rational zeros in the polynomial, but through synthetic division, and be on the lookout for zero remainders. Okay, like here in example 2, nice easy one. Here is our leading coefficient is 1, our constant at the end is 1. So if we do our rational zero test, the constant at the end here, let me use red ink, the factors of 1 are plus and minus 1. And then blue ink, our leading coefficient is also 1, so that's plus or minus 1. So all possible combinations here would be 1 divided by 1 is 1. 1 divided by negative 1 is negative 1. And if I switch those, I'm going to get the same positive 1 and negative 1. So these are the only possibilities out there. Now, we can't really factor this, but what we could do is synthetically divide, or we could just run these numbers through the function. We can do f of 1 and see what comes out. We can do f of negative 1 and see what comes out. We're on the lookout for zero remainders. So remember, this is x to the third. That's supposed to be a 3. X to the third plus x plus 1. X to the third plus x plus 1. And in the parenthesis up here goes a positive 1. 1 cubed is 1, plus another 1, plus another 1. Well, that's equal to 3. If this was a zero remainder, then 1 would have been one of our solutions, one of our rational zeros, but it's not. We have a remainder. Let's try negative 1. Negative 1 cubed is negative 1, plus another negative 1. That'll take us to negative 2, and then plus 1 will take us to negative 1. So another remainder. So that means that this equation has no rational zeros. I bet there's some irrationals in there. We're guaranteed 3 linear factors, 3 zeros, but none of them are going to be rational. Ooh, let's see the picture of this one. Here we go. So it does cross the x-axis at one point between 0 and 1, but again, that's an irrational number. The rational zero test is only going to work for rationals. All right, here's a little practice problems for you. So what you should do is pause the video and try these out, and then fire the video up and see what worked out. Ooh, now let me see here. I wonder if I should give you a hint for number 2. Because in class, we could do something like this on the TI-89. All right, so pause the video for the first one and then fire it back up, and I'll walk you through how we would do this on the calculator. Well, at least for this, list the possible zeros, and then we'll figure out how to test them here in the video. All right. Okay, for the first one, determine the number of zeros of this polynomial function. Since it's x to the fourth, it has 4 possible zeros. Okay, now for the second one, let's list our possible rational zeros. So up top, we're going to do the factors of 4 or negative 4. So it's always plus and minus. Plus and minus 1 goes into 4. Plus and minus 2 goes in there, and also plus and minus 4. Our leading coefficient is just a 1, so that's plus or minus 1. So it looks like we have 6 possibilities. positive negative 1, positive negative 2, positive negative 4. Now we could, this would be a little long, we could do synthetic division on each of those, or there's another way to do it if we did a table on the TI-89. So here, let's pretend we're in class and you're working on a TI-89. We've got our x values, positive, negative 1, 2, and 4. We're going to plug those into the equation to see what comes out. So we will evaluate these. You could do it, longhand, but with a TI-89 it's so slick. So let's do it like this. We'll start at negative 4, do negative 2, negative 1, 1, 2, and 4. We're looking for 0 remainders, or maybe where even the sign changes from positive to negative. So if we put negative 4 in the equation, out pops a negative 60. If we put in a negative 2, the y value is negative 16. Negative 1 goes in, negative 9 comes out. Now 1 goes in, 5 comes out. Now notice, we've changed from negative to positive. So we went from a negative 9 to a positive 5. That means there's a 0 in between these numbers somewhere. 0 between negative 1, positive 1. Somewhere in that interval there is a 0. Well, let's plug in 2. In goes 2, out comes a 24, another positive number. Put a 4 in there, out comes a 116, another positive number. So it looks like here we have no rational zeros, but we did figure out where one of the irrational ones would live. It's not going to help us find it, but it is in there somewhere. All right, example 3. Find the rational zeros here. Okay, well, let's do our fraction. Our constant at the end is 6, so the factors are plus minus 1, plus minus 2, plus minus 3, plus minus 6. Thankfully, our leading coefficient is a 1, plus minus 1. So it's kind of irrelevant to the problem. So we have 8 possibilities, positives and negatives for 1, 2, 3, and 6. So what we would do here is just start synthetically dividing, looking for a 0 remainder. And once we find one 0 remainder, it might make it easier to factor what's left, the remainder of it. So let's just take a shot in the dark here. I'm going to just try positive 1. And my coefficients for synthetic division, 1x to the 4th minus 1x cubed plus 1 minus 3 minus 6. So we're going to go like this. Drop down our 1 and we multiply and add. Multiply and add. Multiply again, we get a 1. That's a negative 2. Negative 2 times 1 is negative 2. Negative 8. So that didn't work. 1 is not a factor. So that took us down a dead end. Let's try negative 1. Negative 1. So bring down the 1 here. Negative 1 times 1 is minus 1, and we add to negative 2. Multiply there and get a 2. That adds up to a 3. Negative 1 times 3 is minus 3. Ooh, and that adds to negative 6. Here we go. Negative 1 times negative 6 is plus 6. 0 remainder. So we got it. Let's see. We started with x to the 4th, and we divided out an x. So this one is 1x cubed minus 2x squared plus 3x minus 6. Now, we've reduced it a power. It might be easier to factor. And since I'm looking at this, it looks like it might be a factor by groups. So let me move this up here. If we group off the first 2, we can factor out an x squared, leaving an x minus 2. Oh, this looks like it's going to work. We can factor out a 3, and that'll leave an x minus 2. So now, out of the brackets, we can factor out that x minus 2 factor, and that will leave us x squared plus 3. So the directions were find the rational zeros. So we're getting close. Oops, get over there. All right. Ooh, now I don't want to forget -1 did work, so we've had x plus 1 here. Yeah, that was our first factor that we factored out. So if we have it factored all the way down here, we can set this one equal to 0, and we get x is -1. And if we set this one equal to 0, we get x is 2. And those are both on our list. So we found a couple of them. And then if we look at this one, x squared plus 3 is equal to 0. That would be x squared equals -3. And when we take the square root, at least the negative can escape as an I. X equals plus or minus imaginary component times the root of 3. Okay. Ooh, there's a remark down there. Ooh, let's look at the graph. What's the graph look like? Okay, we found these two. That's where we crossed the x-axis. Remember, our other ones were imaginary, so they're not going to be crossing the x-axis there. And the remark, when there are few possible rational zeros, as in example 2, it may be quicker to test the zeros by evaluating the function. When there are more possible rational zeros, like example 3, the one we just did, it may be quicker to use a different approach, such as synthetic division or sketch the graph. All right, when the leading coefficient of a polynomial is not a 1, the number of possible rational zeros can dramatically increase. In such cases, the search can be shortened in several ways. If you got a graphing utility, it might speed up the calculations. If the graph is provided, you can get some good estimates of the locations of some zeros. The intermediate value theorem with a table of values can give you approximations of zeros. And synthetic division can be used to test those possible rational zeros. After finding the first zero, the search becomes simpler by working with the lower degree polynomial obtained in the synthetic division. As we saw in example 3, as soon as one value worked and we got a zero remainder, we put back in the x's and factored it with another method. So let's see what's going on here in example 4. I think this is the last example for this video. Ooh, and this looks like it could be juicy. Find the rational zeros of this. So our constant at the end is 3. So the factors of that, plus minus 1 and plus minus 3. Leading coefficient, 2, also prime, but it does have a couple of factors, plus minus 1, plus minus 2. Now let's list these out. I'm going to start here with this numerator and give it each of the denominators. First I have 1 over 1, and that'll be a plus 1 or a minus 1. And then I'll have 1 over 2, so that's 1/2, plus or minus 1/2. Now let's use the 3. We can do plus or minus 3 over plus or minus 1. That's just plus minus 3. And then we can do plus or minus 3 over plus or minus 2. That's 3/2, plus minus 3/2. So that's a lot of possibilities. Let me get a little more room here. So we're just going to take a shot in the dark, pick one, and synthetically divide, and hope for a zero remainder. So let's see, we've got cube, squared, first power constant, nothing is missing. So that's a 2, a 3, a -8, and a 3. And I just like to always start with positive 1. Let's see what happens. Bring down our first 2. 1 times 2 is 2, and we add. 1 times 5 is 5, and we add. Oh, jackpot. 1 times -3 is -3. There is our zero remainder. So we started out with a 2x cubed. We divided out a 1. So an x minus 1 is one of our factors. And then what remains, let me switch to red ink, this 2 will now have 1x, or x to 1 power lower. So now that's a 2x squared plus a 5x and a minus 3. Okay, I could keep plugging and chugging with these, but let's just take a look at this and see if we can figure it out. We've got our x minus 1 factor. So 2x squared can only come from 2x and x. Now let's see, we've got a minus at the end and a plus in the middle, so let's see, The factors of 3 are 3 and 1. If I put my 3 here, that's going to hit the 2. That will give me a 6. And if I make that a plus 6, I need a minus 1 to get me to 5. So let's double check those outers. That would be a positive 6 and then a minus 1. 6 minus 1 is 5x. And then it multiplies to the negative 3 at the end. So we got it. So if we set this equal to 0, we can now find our rational zeros. Remember, when this problem started, it's 2x cubed, so we should have 3 of them. And if we set x minus 1 equal to 0, we get x is 1. If we set 2x minus 1 equal to 0, we're going to add 1, 2x equals 1, and divide by 2. X equals 1/2. That was one of the numbers on our list. And now here, x plus 3 equals 0 means x is negative 3. That's also here on our list. If we had tried the 3 halves, positive or negative, it would have been a waste of time. Remember, when you find the rational zeros of a polynomial function with many possible rational zeros, as we saw in example 4, you must use trial and error. There's no quick algebraic method to determine which of the possibilities is an actual zero. However, sketching a graph might be helpful. So here's the last huddle problem. The first one, I guess it's find the rational zeros. Find the rational zeros. So here are a couple of hints for you. On this first one, I'm using red ink here. List all the possible rational zeros. And then when you start testing them, I'll give you the hint that all the zeros are positive. Don't try a negative number. For the second one, you're going to list out all the possible rational zeros. There's quite a few of them. I think there's maybe a dozen total. The first one you should try is positive 1/2. And then you'll take your third power equation and get it down to squared. And then once it's squared, you can do another method like the ACB method. So pause the video, use these hints once you find all the possibilities, and then find all those rational zeros. Pause the video. You didn't pause the video, did you? Okay, this one. Our constant at the end is negative 125. So what numbers divide perfectly into 125? Well, 1 does. Since this number ends in a 5, plus minus 1, plus or minus 5. Think money. $1.25 is divisible by quarters, so plus or minus 25. And I'm not going to have room to squeeze it in there, but you can write it on your paper. Plus or minus 125. A number is always divisible by itself. Okay, let's set up our synthetic division. Coefficients 1, negative 15, positive 75, negative 125. Okay, if you tried 1, 1's not going to work. But 5, bring down the 1. 1 times 5 is 5, and we add, get negative 10. 5 times negative 10 is negative 50. 75 minus 50 is 25. 5 quarters are $1.25, and there's our zero remainder. So 5 is a factor. If 5 is a factor, that means if 5 is a solution, then x minus 5 is a factor. And what we're left with from our synthetic division is 1x squared minus 10x plus 25. Can we factor that with another method? Well, two numbers that add to negative 10 and multiply to a positive 25. This shouldn't be too difficult. X squared has to be x and x. Negative in the middle, last term is positive, means we have to have minus minus. And then the numbers that add to 10 and multiply to 25 are 5. Ooh, look at that. It's the same factor 3 times. So this is x minus 5 of multiplicity 3. So when we were doing our synthetic division, once we tried 5 and it worked, doesn't mean it's not going to work again and again. You can have multiple factors. If you try every possibility and you think you're out of options, go back and try the one that worked a second time. Okay, now for this one, let's see here. Just listing all these possibilities is quite a chore. Our constant at the end is 6. The numbers that divide into 6, plus minus 1, 2, 3, and 6. Denominators will be the factors of 2, plus minus 1, plus minus 2. All right, I always like to start up here in the numerator, so we're going to have 1 over 1 and 1 over 2. So plus minus 1, plus minus a half. Let's go to the 2. 2 over 1 and 2 over 2. Well, 2 over 1 is 2, and then when we did 2 divided by 2, well, that's plus or minus 1. We already have that accounted for, so we're not going to write it again. Now let's use the 3. So here's 3 over 1 and 3 over 2. Plus or minus 3, plus or minus 3 halves, and the 3's done. Now the 6. 6 over 1 is 6. 6 over 2 is 3, and we already have 3. So plus or minus 6. So when we have positives or negatives, there's 2, 4, 6, 8, 10, 12 possibilities. You know, that's quite a bit to start guessing and checking on synthetic division. Luckily, I am such a nice guy. I gave you a hint that you should try positive a half first. So our leading coefficients are 2, 1, negative 13, and 6. We will synthetically divide a 1/2. We bring down our 2. Half of 2 is 1, and we add. Half of 2 is still 1, and we add negative 12. Half of negative 12 is negative 6, and we add and get a 0. So 1/2 is a solution. That means x minus 1/2 is a factor. And then we're left with, we've got a 2, but now our power dropped by 1. That's a 2x squared, plus a 2x, and a minus 12. Ooh, hold on, did I? Ooh, I thought I made a mistake, but I did not. Let me back that up. There we go. Okay. Now, factoring this, I notice everything has a 2 in it. They're all even. So what we can do, let me switch to blue ink. I'm going to factor a 2 out of there, and I'm just going to put it here in front of this. So I've got 2, x minus a half, and then that'll leave an x squared plus an x minus a 6. Now that'll be a little easier to factor. Ooh, and watch this. You know, if you don't like this fraction, here in this factor, let's distribute the 2. So 2 times x is 2x minus 2 times a half is 1. Now, this is x and x to get the x squared. What factors to 6? 1 times 6 or 2 times 3. And we want to add those to get a positive 1. So that'll be a plus 3 and a minus 2. If I did not erase my list of all possible factors, x equals negative 3 was one of them, and x equals 2 was one of them. But remember, there were a dozen in total. So using synthetic division once to get the party started was pretty useful. And I think that's the end of the video. Watch WebAssign for the assignment. The next time I see you in class, we'll do some odd problems for practice.